Hi, welcome back to my statistics class. So today I'm going to break down the step by step and how to make a hypothesis test. So step one, you need to state the null and alternative hypothesis. So what is a null hypothesis? Null hypothesis, we use the notation S sub O. The null hypothesis is the carbon value of the parameter, the accepted value or the statistical, which is the assumption that we have, which is the assumption that we have for the population proportion. So usually this is we use null hypothesis equals to certain number, such as our previous example, the scenario is our p is equals to 0.5, which is 15% of the chance. We assume that this is a fair coin, so the probability of heads up should be 50%, which is 0.5. So the alternative hypothesis, we use the notation as H sub A. Sometimes they use H sub 1. The null hypothesis is what we were trying to prove. Sometimes it's greater than the number, sometimes it's less than the number or not equal to number. We would not state that, hey, the alternative hypothesis equals to certain amount of number. For example, in the previous example, also the flipping the coin, we would not say, hey, the null hypothesis is equals to 0.75. This is not right. It's always either greater than, less than, or not equal to. We don't want to give them an exact number. So when we use the greater than, when you see those keywords such as larger, increase, more than. So for less than a number, we use such as we're trying to prove that, hey, our sample distribution is smaller than our assumption, or decrease, or less than. So what is not equals to? That means it's different from what we are trying to prove. Those are the keywords. So now here are the example. So an oaticid provided relief for 70% of people who use it. Our pharmaceutical company has a new drug that they want to test to see if it is more effective. So now keyword test. That means we are going to use the hypothesis test to run the experiment. So what would be our null hypothesis? Our null hypothesis would be what? Here, 70%, right? 70% of people who use it. So P is 70%. So 70% of people who use it feels that, hey, relief after they use the antisect. Okay, so what would be the alternative hypothesis? So alternative hypothesis is something that we are trying to prove. When trying to prove, look, the last sentences. See if it is more effective. More, that means greater than the same number, which is P sub 0 is greater than 0.7. Okay, so on this sample and distribution, we have a 0.7 and then 1 standard deviation. I don't know what's that yet. And then 2 standard deviation. Think about it, it's more than. So this is minus 1 standard deviation and minus 2 standard deviation. So think about more than. So that means the p hat is going to be on the left, because to the left is greater number, to the right is smaller number, more than. So we have a p hat on the left. So we're trying to prove this area. That would be our p-value. Also, this is called Rydell test. Okay, so now the next one. Second example, a company is concerned that too few of its cars meet the population emission standard. They have 1,500 cars. They sample 56 cars and find that 43 meets the emission standards. They want to test if less than 80% of their fleet meets the emission standard. So what would be the hypothesis? The hypothesis should be this one, right? 80%. So that is the assumption. They assume that, hey, 80% of the car meet their emission standard. So would be 18%. What would be the alternative? Alternative would be, look at the keywords. The keyword is less than. So that means should be P less than 0.8. Let me change the color. Let's use yellow. Okay. So now again, we're trying to make a sample distribution. But remember, always you need to do the standard deviation first. The central limit theorem first. So we have subtract 1 standard deviation, subtract 2 standard deviation, and subtract 3 standard deviation. On the right side, we have add 1 standard deviation, add 2 standard deviation, and add 3 standard deviation. So look, if it's less than, should be on the left side. So our p hat may be around here. We don't know yet. So let's assume that it's here because the less than is always on the left. It's less than 0.8. So remember, the left is subtract, the right is add. So that's why less than is on the left. So here we're trying to prove this area. This is going to be our p-value. So this is on the left side. So also it's called left tail test. Okay, so now look at example number C. In 2014, the official poverty rate was 14.8% in the US. A city official wants to test if their county has the different poverty rate than the rest of the US. So again, this is test. That means they want you to, this is indication that, hey, we're going to use a hypothesis test. And then what would be our null hypothesis? Our null hypothesis is the population, which is our sample distribution is going to equals to our population. Okay, population proportion, which is 14.8%. Usually it will be better, you can convert it to a decimal. So we're 0.148. And then alternative hypothesis was what? So a city official wants to test if their county has a different means it's not less than or greater than. So it should be alternative is not equals to 0.148. So when we build a sample distribution around that assumption, we have 0.748 at 1 standard deviation, 2 standard deviation. Here subtract 1 standard deviation, 2 standard deviation. Okay, since it's different, that means p hat could be on the left side or the right side. This is going to be our p-value. You can test one of these. But since our normal distribution is symmetric, that means our p-value is going to times 2. These two areas should be the same. So that means our p-value needs to times 2. So this is also called two-tailed test. Okay, so what's the next step? The next step is how do we set up the sampling distribution? So always remember the first thing you need to do after you state the null and the alternative hypothesis. The second thing to do is to check the central limit theorem. 3 things: independence, randomization, and the success and failure condition. So again, I'm going to emphasize this again. I know I said it many times. So since our hypothesis test is trying to build around the null hypothesis, when you test the success or failure condition, it has to be times the sample size times the null hypothesis. Greater than or equals to 10. The 0 means the null hypothesis. Okay, step 3, set up the sampling distribution of proportion and calculate the test statistic. So these two is 2 different methods, but you should end up with the same result. Okay, So let's look at what is sampling distribution. We have the mu is going to equals to our null hypothesis, and the sigma equals to square root of P naught Q naught divided by sample size. So for test statistic, we have our z equals to our p hat, which is the sample distribution, subtract our mu divided by sigma. And you need to remember that our mu equals to our null hypothesis, and the sigma equals to square root of the p naught p sub 0 times q sub 0 divided by n. Okay, so let's look at the example. So for each of scenario below, set up the sampling distribution and calculate the test statistic. So we have an old antibiotic provided relief for 70% of people who use it, and pharmaceutical company has the new drug they want to test if this is more effective. So assume that n is equals to 50, p hat equals to 0.75. Okay, so we have p naught is 0.7, right? And we already stated the null and hypothesis test in the previous example, so we don't need to do that. So now we're just trying to set up the sampling distribution. We know that the mu is equals to p naught. So we have mu, or maybe we should write down all the important information first. 70% is the p naught, which is our null hypothesis proportion. And then sample size n is equals to 50. P hat is equals to 0.75. 0.75 means maybe from the sampling distribution, from the sample, they found out that, hey, 75% of people from the sample distribution use it and found that it is relief. Okay, so mu is going to equals to p naught, which is 0.7, and then sigma equals to p sub 0, q sub 0, divided by n and take square root of the whole things. So p sub 0 equals to 0.7, q sub 0, which is 1 minus 0.7, which is 0.3, divided by n, which is 50, and take square root of it. Okay, and then now we also need to test the z statistic. So z statistic would be z equals to p hat subtract p sub 0 divided by sigma. Oh, I forgot to calculate that. So this is, you use a calculator, you will end up to have 0.0648. Okay, so what would be the z statistic? So the z statistic is p hat, which is 0.75, subtract 0.7 divided by sigma, which is we calculated previously, which is 0.0648. Okay, and then you will have a z-score statistic. This is equals to 1.5432. Again, you can calculate it by your calculator. I'm not going to show how to use a calculator. Okay, is that correct? Did I miss anything? Yes, we're missing something, which is we always need to do before we apply to the sample distribution or test statistic. We always need to test, central limit theorem, which is we forgot, we should have done it at the beginning. So this is an independent test, independent experience, and then this is randomization. Yeah, I mean these two. What about the success and failure condition? So again, you want n times p naught, not p hat. Why is that? Because our sampling distribution is built around the null hypothesis. Our null hypothesis is the proportion is equal to 0.7. So we want to use n times 0.7. So they give you the sampling distribution is 15 times 0.7, which is greater than or equals to 10. And then n times q naught, which is 50 times 0.3, also greater than or equals to 10. So it meets this condition. And then we can start in to set up our sampling distribution and calculate the test statistic. Okay. B, a company concerned that too few of the cars meet the pollution emission standard. They have 1,500 cars. They sample 56 cars and found that 43 meet the emission standards. They provided the test if less than 80% of the fleet meets the emission. The first step is you try to identify the important information. So let's take a look. 80% is our null hypothesis, which is our assumption that 80% of the car meets the standard. But what was the p-hat? The p-hat is by the sample distribution, sample experiments that we have this part. They sampled 56 cars and found that 43 meets the standard, so which means our p-hat equals to 14.3 divided by 56, which is equals to 0.7679. So what would be our sample size? Again, from the highlighted yellow part, we know that our sample size is 56 cars. So what's the first step when you try to set up a sampling distribution? State the central limit theorem. So from the central limit theorem, we have independence, randomization, and then success and failure rate. Again, this is built around the null hypothesis. You want to use the sample size, which is 56 times 0.8, which is greater than 10, and then use the failure rate should be 56 times 0.2, which is also greater than 10. Okay, so I call this is noisy information. So what is this? Why this is not the sample size, 1,500 cars? Well, they made 1,500 cars each year, right? A company makes, they have 1,500 cars. This is not their sample. This should be their population sample, so population size, not the sample size. This is the sample size. But we don't need to use our population size. That's all of the car. That's part of the car from the population. So that's why we call this is a sample size. So you need to identify which one are the useful information. So that means we don't need to use 1,500. Okay, so now let's continue to set up our sampling distribution. Okay, so we have mu equals to our null hypothesis proportion, which is p hat, which is 0.8, sigma equals to p sub 0 q sub 0 divided by n, which is 0.8 times 0.2 divided by 56. And then we use a calculator to calculate our sigma is equals to 0.423. Okay, so what about the test statistic? Test statistic is we use z-score, which is we use z equals to p hat subtract p sub 0 divided by p naught q naught divided by n. Basically, it's our mu and sigma, but p hat is equals to what? P hat we just calculated, which is 0.7679 subtract 0.8 divided by our sigma, which is 0.423. So our z-score statistic equals to negative 0.6005. Okay, C. So the official poverty rate is 14.8% in the US. A city official wants to test if the county has a different poverty rate than the US. Okay, so we're missing some information. I'm going to make up some, which is we have the sample size. Let's say we test 300 of household, and then we find out that, hey, 12.8% of them, 12.1% of them are poverty. Okay, so now we have what? We list all the important information. We have a p sub 0, our null hypothesis, equals to 0.148, p hat equals to 0, 1 to 1, and then sample size equals to 300. First thing is test central limit theorem. So independence, randomization, and the success failure condition. Again, you want to times the null hypothesis proportion, which is 300 times this guy, 0.148 greater than or equals to 10, and then the failure rate would be what? 300 times 1 minus 0.148, also greater than or equals to 10. Okay, so now it meets the center limit theorem. Now we can set up the sample distribution. We have our mu equals to p sub 0, which is 0.148, sigma equals to p sub 0, q sub 0 divided by n. So we have a 0.148 times 0.182 divided by 300 and take square root of the whole things. So we got this is equals to 0.205. Okay, test statistic. So test statistic, we have a z equals to p hat subtract p sub 0 divided by our sigma. Let me change this to mu. So we have p hat equals to 0, 1.21 minus 0.148 divided by 0.205, which is equals to negative 1.317. But there's a catch. So what would be the catching? The catching part is this is a two-tailed test. Remember our first time setup? That means whenever we got the p-value, we need to times 2. So that means in GeoGebra, after you find out the area, you want the p-value times 2 when it comes to the two-tailed test. Okay, step 4 and 5 is we testing the p-value and writing down a conclusion. Okay, so let's do some review. In our first example, which is the antecedent, we have a right-tailed test. So a p-value is on the right side. And then the second test is the car emission standard test, which is the p-value is on the left side, which is such as less than, decrease, and smaller. And then two-tailed test is when we have the keywords such as different. We need to times 2 the p-value. Okay, so when do we reject the null hypothesis? And what we do this when the p-value is small. When the p-value is small, remember, because we're trying to build the sampling distribution around the null hypothesis. And then we end up with a p-value. P-value is the percentage of the area, right? If it's really small, that means it's less likely to happen. That means we need to reject the null hypothesis. That means, okay, we can use another way to think about it. When does the p-value going to be really small? That means it's really far off from the center. The further off from the center, that means the less likely to be happen. So when the p-value is small, our assumption or our sample was unlikely under our null hypothesis. So it is statistically significant. We reject the null hypothesis. That means after we reject the null hypothesis, we can say, hey, there's an evidence for the alternative hypothesis. That's something that you need to fill in. We reject what null hypothesis, and we evidence for the alternative hypothesis. What if, when we fail to reject the null hypothesis, when the p-value is not sufficiently small? They can be small but not small. Usually I will give you standard tells you that, hey, when does it consider small, when is considered not small. So I can say our sample could occur due to random variation. So it is not statistically significant. So we fail to reject the null hypothesis. And we don't have enough evidence for the alternative hypothesis. Okay, so now, so far, we've been talking about the, hey, when the p-value is small enough or not sufficiently small enough. So how do we determine it? So now we introduce a new concept. It's called significant level. We use the notation alpha. So alpha is the cut-off value, which is also threshold for which we can reject the null hypothesis. The most common significant level, alpha, is equals to 0.005, which is 5%. Sometimes they use percentage, sometimes they use the decimal. This means we reject the null hypothesis as long as the p-value is below 0.005. You may see the largest significant value. Sometimes they use 0.1, which is 10% of the significant level, when the results don't have a very serious effect. So if they didn't state, sometimes they will have to say, hey, this has to be a really smaller significant level, such as 0.01, which is 1%. So if they didn't state anything, we will assume that, hey, this is a 5% significant level, which is 0.005. Okay, so now let me give you an example. So for example, for our right tail test, this is p0, and then we found out that, hey, our p hat is in here with a p-value of 3%. Let's say this is equal to 0.3. I don't know. I'm just make up some number. So now let's compare p-value and our alpha. So our p-value is equal to 3%. Alpha, let's assume that the default is always, if they didn't state specifically, the default is always 5%. So we have our p-value, since it's 3%, which is less than our alpha, which is our significant level, 5%. 3% is less than 5%. So if it's less than, we will say, hey, our p-value is significantly small. So we can reject our null hypothesis. Alternative, what if I change it? I change, hey, our p-value is, let me use a green pen. We have a p-value here. The green p-value equals to, let's say, 11%. So it's greater than the alpha, right? Because our alpha is 5%. So we can say that, hey, our p-value is greater than our alpha, which is 11%, definitely greater than 5%. So we can say, hey, our p-value is not sufficiently small. So in that case, we fail to reject the null hypothesis. And then we start in state that, hey, we fail to reject null hypothesis, not enough evidence for the alternative hypothesis. Okay, so in the next class, I will give you more example about how to prove the whole hypothesis test, how to write down the proof. See you next time.